So when you look at oxidation and reduction, as I normally say, one of the things that scientists would have really focused on is before they started looking at it in a particular way, the main focus was oxygen and hydrogen. So they would have talked about how these two atoms or elements rather, just a sec, how they would actually interact or involve in a reaction. So when we first or when the scientists first looked at oxidation and reduction, those who don't know, it's redox for short. So whenever you see the redox, that abbreviation or that word, it's really talking about reduction and oxidation. Oxidation, if you look at oxidation, in terms of oxygen, is when something gains oxygen. When we look at it in terms of hydrogen, before scientists actually started zeroing in on the fact that, you know, right now we're looking at some equations and they might not having oxygen and hydrogen. And so they didn't normally categorize those as redox reactions until later on they started to say that, we can focus on the oxidation number and electrons. Oxidation is loss of electrons. And then the thing about compounds or elements, they would have an oxidation state. And they say this is an increase in oxidation state. And so once you're looking at it, we said that not all of the equations that you'll come across may have hydrogen or oxygen. And so one of the major ones as a CXC student that you can basically have a grasp at doing is identifying the oxidation state. And so if you can track the oxidation state of atoms in compounds, trust me, you would be able to determine if something is being oxidized or if something is being reduced. Last week, we ran through the rules of how we assign oxidation number. And so we're going to be doing that a little bit. So we're just going to jump to reduction. And reduction, this is the loss of oxygen. This is the gain of hydrogen. This is a decrease in oxidation number or state. So as a student, if you can remember this, and I normally say to students, once you're able to remember one, and if you notice, it's like they are actually opposite. And so once you have oxidation, you must have reduction. And so if you can recall oxidation, then you should know reduction. So just a tip, just know one. So if you know that oxidation is the gain of oxygen, this is the loss of hydrogen, this is the loss of electron, this is an increase in oxidation state or oxidation number, then automatically you should know what is reduction because they're opposites. So get to know one. Now, a little bit about a background. We know that metals are the ones that when you're engaged in a reaction, metals tend to be the one that lose electron. And so if you notice, it says oxidation is the loss of electron. And so we will know that metals typically will undergo oxidation. So we have to be very, very careful in how we apply this because you can have a metal moving from an ion because you have to know the state. And let me just say, for the background of this topic, you have to be familiar with your ions. Ions are very, very, very critical in this aspect, this topic. It's a prerequisite to know your ions. And sometimes students, don't know the ions, and that's where the challenge comes in. It's not so much the concept of oxidation and reduction. So metals tend to lose their electron. And so metals are undergoing oxidation and reduction. So an atom of a metal is undergoing oxidation. So they're losing electron. Non-metals, likewise, will be gaining electron. And so they are being reduced. And so just to clarify, when you zero in on the electrons, you should remember from your subatomic particles classes that the teacher would have gone through, the charge of an electron, where an electron is located, because you might get little questions along that line on a CXC paper, and it is foundation knowledge. Electrons are basically in the shell, but electrons are negative. And so that will help you in the sense that students will often ask me, why is it that when the compound or the element is gaining electron, how can it be gaining but it's being reduced? How can you gain something and you're decreasing? That no sound right, sir. And so I say to them, what you're gaining or what the elements or what the compounds are gaining, they are gaining something that is negative. So you should have in the back of your head that the electrons are negative. So you're gaining something negative, so automatically you're going to be decreasing. Now in Jamaican terms, in the whole concept of oxidation and reduction, we will also use this little jargon, oil rig. And some students, if they don't remember anything, they remember oil rig. The only drawback to the oil rig is really that it focuses on the concept of electron. So if you can remember oil rig, then you know what is happening with electrons in terms of oxidation and reduction. So oil means oxidation. Maybe I should write this another way. Oxidation is loss of electrons. And the rig, reduction, is gain of electrons. Yeah? So if you typically want to remember, just remember oil rig. But as I said, it's limited. It won't talk to you about the oxygen. It won't talk to you about the hydrogen. It won't talk to you about the decrease in oxidation number or increase. Then you will just be focusing on the electrons, which automatically most of the time, if you can, they ask you a question along that line. So it's just limited in terms of giving you information about the electrons in terms of oxidation and reduction, but it is something that can help you. Now, in order for you to deal with, as we said before, oxidation and reduction, and this is what I recognize with students. You see, you have to, when you gain the knowledge, you bring it across. So I start normally by dealing with compounds, because in in chemical equations, you're going to have compounds. So they will basically be forming the chemical equation, a part of the chemical process. So you won't see them individual. So while we will look at how we deduce the oxidation state of the carbon in carbon dioxide, remember carbon dioxide is not going to stand alone. Say for example a combustion reaction, when a organic compound burns, you're going to get carbon dioxide and water. So you're going to have different compounds in a reaction. When a metal reacts with a acid, you get a salt and hydrogen gas. So you're going to have those different compounds within the chemical reaction. So we're going to quickly learn how to assign or determine the oxidation state. What are some of the rules? So the first rule, so all elements that are not bonded to another atom, they have an oxidation number of 0. So whenever you see an atom that is not bonded to another element, and prime example, we have the 7 diatomic. So the 7 diatomic elements, even though they're bonded to a same atom, they fall into this category as well. So say for example, hydrogen gas is looking like that. So when you talk about the oxidation state is 0. All the diatomic. If you remember all 7 of them, the oxygen, the nitrogen, the group 7, the chlorine, the fluorine, the bromine, the iodine, and the hydrogen, they, once you're looking at their diatomic elements, you are going to have them having an oxidation state or an oxidation number of 0. Likewise, a metal, and I just spoke about that. If you're looking at an equation where metal is reacting with an acid, and we know that metals are solid at room temperature, right? This magnesium is going to have an oxidation number of 0. And it has an oxidation number, and I was explaining to a class yesterday, you have to remember that, and I see a lot of students making this mistake, so I can even highlight it here. The atomic number is not a measure of the protons and electrons. So a lot of times, because as teachers, or you will see in the book, yes, in an atom, the same number of protons is the same number of electrons. But oftentimes when students are writing the definition for atomic number, I'm not sure why they're including that it's the same, it is the number of electrons and protons. No, if you are doing that, that's incorrect. So going back to why magnesium here would have an oxidation number of 0. Remember, the atomic number is a representation of the proton in an atom. Also remember that the proton will never change. It's the signature of the atom. Electrons, on the other hand, while you're talking about the atom, we say that yes, you will have the same number of electrons as proton in an atom. And so the atomic number for magnesium would have been 12. And let me just remind you that this is something you should know for the first 20 elements. One of the questions that will appear on your paper coming May is a high possibility, 80% chance that you'll get about atomic structure. There's always an atomic structure and bonding. And where they will target you to give information or to show is between the first 20 elements. So at this question, they won't give you any information regarding the atomic number. They are expecting you to know that magnesium is 12. So that's another thing as a student right now, you should know the atomic number for the first 12, sorry, for the first 20 elements. So going back, 12 protons, that simply means I'm dealing with an atom, so you have 12 electrons. Going back again, protons are considered to be positive. Electrons are considered to be negative. Both of them would be cancelling out their charges. And so the atom is considered to be neutral. So since it is neutral, there's no difference in that oxidation state. So the oxidation state is also going to be neutral, which is 0. So the oxidation state of an atom or an uncombined element that is not bonded to another element is going to be 0. So if you have calcium, if you have sulfur, once the element is not bonded to another element, you will have the oxidation number of 0. So the next point, the oxidation number of a monoatomic ion. Remember, we have both cations and anions. We need to remember that when we talk about them, we're talking about, when we say mono means one, and the other version of it would be a polyatomic ion, where you have more than one atoms. Now for the monoatomic ion, and this is why I said that knowing your ions is a plus. We know, and we can look at magnesium again. The magnesium ion would have been a 2 plus. And once we see that ion, certain things should come into our head. I'm just doing a little background. You should know one. It simply means that magnesium would have had 2 electrons in its outer shell. Because this is saying that magnesium lost 2 electrons. That's why it have 2. So if it is that in the atom you had 12 protons, 12 electrons, and magnesium lose those two, then now you have 12 proton and 10 electron. And I'm mentioning that to go back to the point is that you cannot use electron to determine atomic number because the electron can change. So if you say it's the same number of electrons in an atom, then you're going to have a problem because the atom of 12 while the ion of 10. There's a change in the electron. So you cannot use that. While for the proton will always be the same. In the atom or the ion, you will always have 12 proton. So I hope you understand that. Now, please note, for the ion, we write the number before the charge. So a lot of times, even as teachers, and I won't lie, you might be writing and you write the plus 2. No, you should not do that. If you're talking about the ion, the number or the magnitude comes before the charge. So magnesium ion is 2 plus, but the oxidation number of the magnesium ion is plus 2. And again, you would see the connection because this magnesium ion would have now had 2 more protons than electron, and so it has that oxidation, that state that it is in. It is in a plus state, a plus 2 state. So if you know the ion, basically you should know the oxidation number. You can't go wrong. Once you know the ion, you must know the oxidation number. And that again brings us to the link between the both. If you don't know the ion, you're going to run into problems when deducing, trying to work out the oxidation number of elements in a particular compound. Because if you didn't know what, say, magnesium is a 2 plus, maybe you would have said that the oxidation number is a plus 1. And this doesn't only work for cations. So let's look at nitrogen. So nitrogen, the oxidation number, the state of the ion is a 3 minus. And so we can talk a little bit about this. It simply means that this nitrogen would have gained 3 electrons. So the opposite happened. So who can tell me what's the atomic number for nitrogen? And the first question this mega asks from morning. Atomic number for nitrogen.
10. Maybe n minus 3.
No, the atomic number. What is the
Seven.
atomic? Come on.
7.
7.
7.
And so we know that in that atom, that before it becomes an ion, you have 7 electrons because as we said in the atom, you would have basically have the same number of protons, which is 7, same number of electrons. But that is not the case with the ion because this ion would have gained 3. It gains 3 electrons. So now you have, and we can talk about it right here again, why we consider it to be a reduction even though we're gaining. So we're gaining, the nitrogen is gaining something that is negative. So while the protons remain the same, which is 7, you now have 10 electrons. And so you have 3 more negative things than the positive things. So that's why the nitrogen ion is a 3 minus. And so if you didn't know that, then you might run into problems to determine the oxidation number for the ion of the nitrogen, which is, as we said, all we do is to write the charge first. So the oxidation state of the nitrogen ion is -3. And it doesn't get any simpler than that, guys. So that's the next rule. So once you're looking, and again, for heaven's sake, you're not going to have these like that. So let me give a prime example. So like you have this magnesium chloride. The next prerequisite you need to know, and I'm going to say it right here too. I've been saying it, I've been saying it, I've been saying it. The only way you can have a covalent compound is if you don't have any metals present. The moment you have a metal, then that eliminates the concept, because covalent compounds involves only non-metal. So as a chemistry student, you see, once you know your metal and your non-metal, that is also good. But if you come and you see this equation and you don't know that magnesium is a metal, you would be probably ifing and butting if this compound right here is ionic or covalent. So guys, just remember, when we write the formula for compounds, usually you have some different cases, the metals get preference. In organic, the metals get pushed behind. But in regular cases, they're at the forefront. So if you look at the first atom or the first element in that compound and it is a metal, you should just automatically wipe out covalent out of your head. So you just jump and just know say it's a ionic compound. It's that simple. Now, some students just use terms loosely, but I like to ensure that you understand. So when you hear ionic compound, it simply means that is a compound that is made up of ion, a cation and an anion. It can be a monoatomic ion, and you can also have ionic compounds that have a polyatomic ion. But this ionic compound in question basically would have two monoatomic ions. We're seeing magnesium ion and we're seeing chloride ion. So automatically, if you're to deduce the concept of the oxidation state of the magnesium and the chlorine, one of the rules that you can go back to, and that's why we're going through these rules. The monoatomic ions, we just know the charge of the ion. And then you know the oxidation number. So in magnesium chloride, the oxidation number of the magnesium, is a +2, and that of the chlorine is a -1. And so we're good with that. Now, students sometimes ask me, but sir, there are two chlorines. When you're looking at the oxidation number of a ion in a compound, we look at 1. We're always looking at 1. But the overall charge of the two chloride ions is going to be a -2. But when we're talking about it, when you're looking at it, it's on an individual basis. So the magnesium would have been a +2. If you have a compound that having two two cations is the same concept. You're looking at only one. Jump into another rule. We know that oxygen always have an oxidation number of -2, except when in a peroxide. And one of the popular peroxide that we will look at is hydrogen peroxide. In this case, we'll assume an oxidation number of -1. So if CXC, the only peroxide that you'll get is hydrogen peroxide. But otherwise from that, oxidation number of oxygen is always -2. And we're going to see how we can deduce hydrogen always so hydrogen always have an oxidation number of +1, but if it is bonded to a metal, it's going to take on a -1 charge. So those are two rules you need to remember about oxygen and hydrogen. You're good. Next rule, the sum of the oxidation number of all the atoms in a compound, let me say a neutral compound, is equal to 0. And we can use the same concept with the magnesium chloride, the sum of all. So here is the thing. We're now saying that when we add up all the oxidation number in the compound itself, so we're taking into consideration this time, let's see if I can just move this. Can get this down here. This time we're taking into consideration the two atoms of chlorine. So we really look into it. It is a +2 with a -2. And if you're not sure how we get the -2, remember I told you that when you're looking at the oxidation number, we're looking at one of the atom. But if we're in this case, when we say we add up all, the sum of all the oxidation number in the compound should be equal to 0. We're going to see how we can use that later on, because we do have some compounds, or some elements rather, that tend to want to change their oxidation number depending on who they're bonding with. I love hopscotch. So that is it. So if you have a neutral compound, and a neutral compound is one where you're not seeing a charge. So because what will happen is that, again, just like with what is happening in an atom, if you notice, the charges of these two ions, the cation is a +2 the anion is a -2, and so they're canceling out each other, which brings them to being at 0. So once we have a neutral compound, so you won't have a charge of the overall magnesium chloride to be negative or positive, because both charges of the ions are canceling out each other, bringing it to 0. And not even, I think I should be at what, 6? The sum of the oxidation number of the atoms in a polyatomic ion should equal to the charge on the polyatomic ion. And again, your life will be easier in chemistry. 1 second.
Yes.
So I was saying the the chemistry life becomes easier once you know those ions. And so again, we have some polyatomic ions. We have only one polyatomic cation. Anybody knows that polyatomic cation? I always talk about it. Only one you need to know for CXC. Anybody knows it?
Ammonium.
Wonderful. What is it for the ammonium ion? Since I'm talking about an ion, a polyatomic ion, this ion must have a charge.
+1.
All right. Well, as I said before, see, normally it's really a plus. Really, we don't write the 1, so really the 1 would have come before. It's really a 1 plus for the ion. So the thing about it, for this, what they're saying is that when you add the oxidation number of all the concept of the ions, or the atoms rather, in this, it should equal not 0, but the charge. And so the charge, when we add up the nitrogen and the hydrogen, we should get +1. Now, here's the thing, and I spoke about those elements. Nitrogen is a problem element. And we have some elements that give problem. Anybody is a problem student to them teacher. So we have those elements that create some, you can't just look at them and say, oh, me know them oxidation number, you know. It's not like oxygen and hydrogen where you basically just have one exception to their rule. So nitrogen, carbon, sulfur, them are the main ones. They tend to change their oxidation number. So you have to watch them when you see them in a compound. So even if you did work out something and you realize that the nitrogen are 1 +2 or 1 negative, maybe the next time you see it, you don't have that. It probably have a positive, or it have a 3, or it have a 4. It all depends. So there is a little algebra expression, and I really don't like the fact that it's so simple, and students normally say, sir, but you're the teacher. But it's something that going through school, you would have learned how to, so everybody know about solving for X. So at the end of the day, that's what you just basically apply. So like right here, usually we work with, so say for example, CXC says what is the oxidation state of the element underlying. And they will underline the nitrogen and not the hydrogen, because the hydrogen is easy. We know that hydrogen is a +1 unless it is bonded to a metal. And right here it's not bonded to a metal, it's bonded to a non-metal. So we automatically know the hydrogen is that. We cannot do that decision for the nitrogen. So even though in reality we would say a monoatomic ion, right? We would have thought, and we can use that as an example, we would have think sometimes, and we're going to be using different, I'm going to be using two examples to show you. We think sometimes that nitrogen will always be a -3 as the oxidation number. That's not always the case. So what we do is call nitrogen X. We don't know what it is. And we said that we're going to sum them, so we're going to add them up. We know that we have 4 hydrogen, and each hydrogen is a +1. Yeah? And when we add those, we say that it should equal to the charge of the polyatomic ion, which is +1. So when we really look at this, what we recognize, we get X plus 4 equal what? You know them there. Equal what? I second time me or the third time me ask one question. So is it that we're not engaged and we not follow? You not hear me?
Yeah, so if x plus 4, and I know that each one, oxygen is 1, that is equal to plus 4. So x plus 4 equal
No
to
man, we're continuing the equation. I was just testing to see if persons were following. So complete this. We say X plus 4 equal +1.
4 plus
+1.
1.
And then we said that we want to get X by itself. So X plus 4 minus 4 is equal to +1 minus 4. So we now end up with X. We now end up with a +1 minus 4. Then we know the X must be -3. And again, so we can plug that up. We know right here the nitrogen is a -3. And for all of the, we're looking at overall now, all of the hydrogens give you a +4. And so the rule says that when you add up all of them, you should equal to the charge, which is a +1. But look at this. Look at this. Same element, same nitrogen. So you know them students, they one class, them come and them negative or be a problem, them give the next class, them come. You know, think it's a little angel you have in your class. Not true. So the same nitrogen in this case, do you think, if you look at it, you might say, oh, so I just work out nitrogen and it's a -3. And also remember that the monoatomic ion nitrogen would assume a -3. Look at this. What type of compound is this? What type of compound is this?
Covalent.
True. But in terms of,
Polyatomic.
can be it's polyatomic what? Can be, you can't say polyatomic ion because it doesn't have a charge. So what type of compound it would be? it would be a neutral compound. Because when you look at it, you're not seeing any charge. Yeah? So I want you to always remember that distinction. While you look at the polyatomic ion up there, for the ammonium, this compound, nitrogen dioxide, is a neutral because we're not seeing any charge. And we should remember the rules. Remember, the rules are in place to help you. We see a lot of things in the media about school rules, but the rules are in place. If you don't follow the rules, you run into problems when you're working it out. So if you don't remember that when you add the oxidation number or apply that rule, or if you don't remember, say another rule that you can apply, oxygen is always -2 unless in a peroxide, then you run into problem. That's why we go through the rules. That's why we have rules to guide you. So here, I'm gonna underline this as well. Let me just say for the students, you're not going to be getting, or the application of this is not for you to have these single out. So while we're doing nitrogen dioxide like this, we're singling it out and working, but remember nitrogen dioxide will be in an equation, a chemical reaction, for you to deduce what is the oxidation number so you can actually track. We soon get to a question. So if you think that the nitrogen here is a -1, let's see what happens. So we call it X again. And we know that oxygen, we have two of them, and each oxygen is -2. We should equal to 0 because it's a neutral compound. With the X plus -2, and I'm not a math teacher, but person should know some principles. We have two unlike signs. We keep the negative. Sorry, should have been negative. Not what I tell me. Remember, we're supposed to multiply this. So we should have had -4. Yeah? Equal to 0. So now, if I want to get x by itself, x minus 4, need to add 4. And if we do that to one side, we have to do it to the other side. And so x is equal to plus 4. You see how Mr. Nitrogen is? He decides to now assume an oxidation state of plus 4. So, prime example again, we did say that it should equal to 0 this time. So when we look at the plus 4, we have two, all of them as we said, we have two, oxygen. Both of them would give you a negative. So we just, you see those elements, as I said before, the ones to keep track of, the nitrogen, the carbon, and the sulfur, they are the ones that tendency to have a change. But you have other elements as well, right? So just to name a few. So sometimes CXC will ask you. So they can give you, I've seen 1 mark questions where they ask you what is the, just to show or deduce or account for the oxidation number of the nitrogen in nitrogen dioxide. And this is just a 1 mark question for you to work out. So we have those rules, we need to apply them. Cool? All right, so let's put what we learn to the test. because, as I said before, this is how we're going to be getting the question. So CXE may give you this equation and says, tell us who is being oxidized, who is being reduced. And you're going to say, what? But sir not teach me nothing like this. Or miss not teach me nothing like that. As I said, you get compounds. So everything right here, you would have been able to assign oxidation number based on the rules that we went through. Everything right here. So if it is that you have to pull the compound and work out the oxidation number for all of them, do that. But to track what is happening, you assign oxidation number. So if you know the oxidation number, then you can tell what is happening, because you're going to look if the oxidation number is decreasing or increasing. And we're starting very simple, because we know if we have an element by itself, it's not bonded, like we're seeing this copper here. What's the oxidation number?
0.
0. And I say, yeah, we are putting, you see where it comes in. And then we look across beside it. We say, wait, so one diatomic element here, nitrogen. What's the oxidation number?
0.
0. You look beside it. And I'm saying, doing these because I'm hoping that these would have been, the easy ones. We know hydrogen. What's the oxidation number when we see it?
1 plus 1.
Somebody was asking a question. Plus 1. And we know when we say oxygen, it's not a peroxide, it's just water. So what's the oxidation state?
Yeah, but take it. 2.
So negative 2. We have to be ensuring that once we have a charge, we have to mention that. The only one we would not mention a charge will be 0. So if we have a number, it must either be plus or negative, right? So we have to make it clear. And remember, when we really deal with it, we put that charge in front. Once we deal with oxidation state, bear in mind, notice we did not say it's a plus 2 for the hydrogen, because we're looking at the oxidation state for one of the atom. One of the atom is plus 1. And again, the whole concept of a neutral, water is neutral because we're not seeing any charge. So when we add those, so it's really a plus 2 plus a negative 2 would have give 0. And so can jump back over this side. We know, want to know the copper. Again, we know that oxygen is a negative 2. Yeah. So because we started down here, so it's going to shift somewhere for us. Delete. Alright. So if oxygen is a negative 2, if it is something that you have to work out, work it out. But you're supposed to can look at it and tell me what is it for the copper. What rule can you use? What rule we can use to determine the oxidation state of the copper?
The one bonded to
Bonded to. You just pause in the statement. So which rule can we use? Maybe if we did have the copper oxide by itself, and we not look for anything else, we would have jumped to get in the rule. And that me realize sometimes with the whole concept, because maybe if me block out all of this and it just a zero in on the copper oxide, then you would have recognized that copper oxide is a neutral compound. And we say that all the oxidation number, when you add the sum of them of the atom, it should equal to zero. The only way we can get zero is if copper is a positive 2. When we add those two, equal to zero, not true? Yeah? Also know hydrogen, again, we know that rule. Nitrogen again here, people. We know so nitrogen is a problem guy. So, see in one case, it would have been +4. In our next case, it's -3. Look at what it is in this case. Well, it's also -3 here because we know this ammonia gas is a neutral compound. So if we're adding all of them, so technically to work out the nitrogen, we know that all of them, all of the hydrogen would equal to a +3. And so the concept is when we add the oxidation number of all the atoms in a neutral compound, we must get 0. So the only way we can get 0 when we add all of them is if the nitrogen is a -3. And so if you notice, we have basically assigned oxidation number every atom in every element of the compounds in this reaction. And this is where I said the application is very vital. Once you can do this, you can deduce any concept about who is being oxidized, who is being reduced. Because what we're going to do is to track the oxidation state. But if you notice about hydrogen and oxygen, their oxidation state does not change. So on both sides, remember I mentioned that if you see me write these equal signs, this is really the reaction arrow. We know we read the reaction from left to right, just like how we normally read. We read from left to right. So on the left, we have the reactants and then we have the products on the right. So we track. So we're moving from left to right, left to right. And I have to say those concepts because sometimes students just don't know. So what you find is that you can track. So we know that the hydrogen and the oxygen is out because their oxidation number isn't changing. Maybe I can include to show. So we're looking at the copper. And so we're seeing the oxidation number moving from +2 to 0. So what is happening to the oxidation number?
It decreased.
And a decrease in oxidation number signifies what?
A reduction reaction.
So we know that we can write that the copper oxide is being reduced. Not true. So we're seeing where the oxidation. So again, the question would have been, CXC could have asked you who is being oxidized. Look at the equation given below. A matter of fact, they could have even started by giving you the worded equation or just give you the reactants because you should know. So they could have just said copper oxide reacting with ammonia, and they can capitalize on that by asking you to write a balanced chemical equation with state symbols. And so I'm going to pause here. Don't think that you don't get a mixture of the questions. Meaning, a question like this, as I just started, can deal with oxidation and reduction, and I can ask you a lot of things. See, I have gas. I can ask you in terms of moles. So moles can be incorporated here. Whole heap of way the question I can go, So I can ask you about moles because I can ask you what is the volume of gas at RTP for the nitrogen, or I could talk about the ammonia. Yeah? So I could have got a route there. I could also go the route of asking you, how do we identify? So what is it that I could use to identify the gas of ammonia or the gas of nitrogen dioxide or nitrogen gas, sorry, not nitrogen dioxide. So the rule about identification or the topic about identification of gases could come in. We can ask you about writing a balanced chemical equation and the state symbols. So this question can capitalize on all of those. So don't think that you might just be getting one aspect and just say, oh, this is oxidation and reduction. They can ask you about that. Them could have involved moles. Them could have involved identification of gases. So that's how CXC will be coming at you in May. So you have to know these things going forward. So we're looking at the other. We have the nitrogen. And we see where the nitrogen is moving from a -3 to 0. What is happening to the oxidation number? What is happening to
It's
the
increased.
oxidation number again?
It's increased.
So it's increasing, it's increased. So we know what is an increase in oxidation number.
Oxidation.
And so we know that the ammonia is oxidized. So I'm going to take it a little bit further now. We have two terms. We have oxidizing agent and reducing agent. So my oxidizing agent is the substance that is causing oxidation to occur. So who is causing oxidation to occur? Who is causing the other compound to have an increase? Oxide. Which brings us to a simple application. Who is causing the other compound to be reduced? The ammonia. So the trick about it, or what you can apply, is that whoever is being oxidized is actually the reducing agent. So they are the ones that is causing the other compound. And let's look at it. Oxidation, we can look at it in terms of electrons. This nitrogen, why would it have the negative in terms of the oxidation number? If you look at it in terms of the ion, it is a 3 minus, right? Meaning it is moving from the ion state back to the atom state. Now, if it is a 3 minus, it means that it would have had 3 more electrons than normal because it would have gained 3 electrons. And those 3 electrons, again, if you go back to bonding, right here. Now, in order for it to become the atom, it has to lose those 3 electrons. And we did say oxidation is the loss of electrons. So we can look at it in terms of that. Also, we are seeing in the compound where the nitrogen has hydrogen bonded to it. And over here, it doesn't. So what happened? The nitrogen lost hydrogens. What is the loss of hydrogen? Again, oxidation. So we're seeing the application not only with the concept, and we could have deduced that easily, but remember, not all equations may have hydrogen and oxygen in them, but this is one. So we could have even looked at it in terms of that. So let's do it again here with the copper. Now, this copper is a +2, which means the ion was a 2 plus, which means it would have lost the electron. But the copper is going back to the atom state. The copper is going back to the atom state, which simply means that in order for it to get back to that state, it would have to gain the 2 electrons that it lost. What is the gain of electron? Reduction. Here, copper is bonded to oxygen, But when we come over to the product side, there's no oxygen, so copper has actually lost oxygen. What is the loss of oxygen? Reduction. And so, even without us working out these, but I have to show you, because guess what? As I said before, not all equations may have hydrogen and oxygen in them for you to be able to track who loses or who gains that and determine. Not all of them is straightforward, why you can look at who the metal and the non-metal and recognize that the metal is gaining, the non-metal is losing, and so you can just simply. So in any case, what you should always know is how to assign oxidation numbers or oxidation state for any atom in any compound in an equation, and you will be able to use that to deduce who is being oxidized, who is being reduced, and who is an oxidizing agent and who is a reducing agent. Any questions? So we just need some interaction now. We're asked to define each of the following in terms of electrons. So in terms of electrons, what is oxidation?
Oxidation is the loss of electrons.
Thank you. Let's still get used to this pen. And what is reduction?
The gain of electrons.
All right. Now, we never touch this, but we can use the worksheet to deal with it. It says classify each of the following reactions as either oxidation or reduction. By reference to electrons, give a reason for your classification in each case. So we're seeing Fe3 plus becoming Fe2 plus. Fe3 plus becoming Fe3 plus. How did it become Fe3 plus? What happened to it?
Loads electrons.
All right. So if I'm at Fe3 plus and I become Fe2 plus, what happened to me?
You gain back one.
Oxidation.
We gain back one electron. And the gain of electron is
Reduction.
Reduction.
also, even though they said look at it in terms of electrons, or by reference to electrons, look at the oxidation state. What would have been the oxidation state of this? If this is 3 plus, oxidation state,
+3.
and if this is 2 plus, oxidation state,
+2.
and what is happening to the oxidation number?
It decreased.
And a decrease in oxidation number.
Is reduction.
So you see, that's how we're applying what we know. We're applying. So we would have given the reason, but remember, we wouldn't give the reason about the reduction. I was just showing you that because the question is really asking you to focus on electron. So what would have happened is that the Fe3 plus would have gained 1 electron to become Fe2 plus. Not true?
Yes, sir.
Now, aluminum, we did speak about this. Metals are solid at room temperature. The aluminum is not bonded to anything. So when it come over here, so to become aluminum 3 plus, what happened to it in terms of electron?
Gain electrons.
Sure? Think about it again. How did aluminum become 3 plus?
No, it lose electrons.
It would have lost electron
Mm.
because again there are two things that there are one main thing that you should jump out at is that aluminum is a metal. The metal are going to lose electron in this case because we're starting with the atom. So anything that is happening to the aluminum, it's going to become an ion, which is a cation, and cations are basically a plus. And we know that they would have been the ones that lose electron. So what is the loss of electron?
Oxidation.
And we're just applying all of what you know. So once you then that is what I'm using to judge that person's understand the topic. But watch me now. What is the oxidation number of this?
Zero.
Why is it 0? Why is it 0?
Because it's not bonded.
Wonderful. See it? Then if you never know them stuff here, and it's not, I recognize that, and I have to say it, I have to do me, when I get students, me love bring them into, because it's not just only to just recite things. When you're able to learn something, is the fact that it will change your behavior and it will change how you view the chemistry. So once I know that you learn it, that's a plus for me. And learning doesn't mean that you can recall it. You're supposed to know the why. So anytime you get anything outside of it, no matter what CXC throw at you, you can actually use what you learned to apply. What is the oxidation number right here?
+3.
And then we said to ourselves, Wagwan yaso. It's moving from a 0 to a +3. So what's happening to the oxidation state?
Increasing.
And an increase in oxidation state is an increase in oxidation state is.
Oxidation.
So even though I just want I added these two to show you that you can look at it in both ways. But the question is really asking you to zero in on the electron. So we know that this is oxidation because
Anyway, just
the aluminum would have lost 3 electron. And we know the loss of electron is oxidation. The formation of the oxide ion when oxygen reacts with calcium, ionic half equation for this reaction. Ionic half equation. Now, look at this. So when, maybe I can come down here so just to deal with it. I'm showing you the full reaction first. Right? Yeah? And working with me? So them say calcium reacting with oxygen. So we know we get calcium oxide. And just to balance this, we have 2 oxygen here. Put a 2 there. Now we have to balance the calcium. We put a 2 here. Now, the question never asks you for this. So when they ask you for the half equation, they want you to show what is happening between half the story. So we don't want to see what happened with the calcium. Who we focusing on? Who we focusing on?
Oxygen.
Oxygen. So we know on this side, the oxygen would have been an O2, right? Over on that side, remember we are focusing on. Now it go back to something. If you have never been to any of the ionic equation classes, I have not taught you ionic equation. Remember when you're writing this as a just to show as an ion or in terms of the oxidation state, just for balancing, we would have 2 of them, right? Now the thing about this, each oxygen right here, each oxygen would have done what? Why did it become a 2 minus? What happened to the oxygen? Talk to me now, people. What happened to the
So repeat your question.
I'm saying we write in the half equation, we end up focusing on the oxygen. So we know the oxygen is moving from the oxygen gas right here. Yeah? I never put in that for this. And it's becoming, they talk about the oxide ion. This is what they're saying. The formation of the oxide ion. So we're seeing the formation of the oxide ion. Now the thing is, I am asking you, what happened to each oxygen here that they could form the oxygen ion? How did they become the oxygen ion? And you can look at the full story. See the full story I don't guess so.
They lost their electrons.
And again, can't make those mistakes. Oxygen is a what?
A non-metal.
And what do non-metals do?
Gain electrons.
Alright. So we know it, you know. So we have to apply. That's what I would say. That's how work with it. So now that we make the adjustment there, what happened to the oxygen?
They gain
Gain electrons.
So each oxygen gain how much electron?
Each of them gain 2, so
So how much
4.
electron in all? 4?
4.
Beautiful. So watch a little trick here now. Watch this little trick. I forgot to do it right. I'm gonna do it above here. Remember that oil rig? Oil rig. When you have reduction, we write the electrons on the left hand side. When we have oxidation, we write the electrons on the right hand side. So let's go again. When we do the oil rig, just a little tip. Reduction, we put the electrons on the left hand side. Oxidation, we put the electrons on the right hand side. And that we're talking about, when we say left and right, you should know that we're talking about the reaction arrow, not true? So, if the oxygen is gaining electron, what type of reaction is this? Now tell me, say gone out on the head already. What type of reaction is this?
Reduction.
Thank you. And there's a reason why I'm doing this. So we know if it's reduction, we write the electrons on the.
Left hand side.
So this would have been plus 4 electron. So this is the half equation that they want. And we said that the reason would have been each atom of oxygen would be gaining 2 electrons. Yeah? So each atom of the oxygen will be gaining 2 electrons. So just remember this little concept. I wonder if you guys jotting down these things. Oil rig, just remember that you write the electrons on the left hand side, oxidation and reduction. Sorry, oxidation, we write it on the right hand side. CXE love to do this. If you notice, the first question would have been focusing on electron. Now they're asking you to determine or defining, sorry, oxidation in the terms of oxidation number. So what is oxidation? So if you come right here and say oxidation is the loss of electrons, you're not getting any mark. Why are you not getting any mark? But you're going to say, sir, but oxidation is the loss of electron. And that's what sometimes students do. Yes, you give a right, it's a correct answer, but that's not what the question is asking you for. It's if we define it in terms of oxidation number. So if you don't do it in terms of this, you can say oxidation is the gain of oxygen. Yes, you're true, that's right. But that's not the answer that they're looking for. Not true. So tell me the answer they're looking for.
The increase in oxidation number.
Thank you. Reduction.
Decrease in oxidation number.
So we know that that is a decrease in oxidation number. All right. Determine the oxidation number of sulfur. Remember we talk about Mr. Sulfur? Him and nitrogen and carbon, them love give themselves problem. In sulfur trioxide, luckily they gave you this. What if they didn't give you that? Would you have been able to write the formula for this compound? What type of compound is this?
Covalent.
Wonderful. And again, to quickly know the difference, look at the first element. It's not a metal. So more than likely, we're looking on the covalent side. Look at the second element, also not a metal. But there's another way. Once you're looking at a covalent compound, and you're seeing prefixes. So if you say try, die, once you hear those, because ionic compounds, you say it easy, ionic compounds don't have prefixes. So the moment you're hearing a die, bear in mind not all covalent you might hear that. So you still need to know the concept of, it being between two nonmetals or more. So if you don't hear a prefix, or if you hear a prefix, definitely you're dealing with a covalent compound. Yeah? So what two? We just learned the rules. What two rule we can use to help us?
Oxygen.
And what is the rule
Um,
about oxygen?
um,
With our oxidation of -2,
Wonderful. What are the rule?
except for peroxide.
Yeah. What are the rule? So we know that the oxygen is a -2. What are the rule we can use to help us?
the oxidation number in a neutral compound should be equal to 0.
Beautiful. And I'm just going to make an adjustment, the sum. So all of the oxidation number should equal to 0. So we work with those rules. So we call sulfur X. We know we have 3 oxygen, each of them -2, and it should equal to 0. We end up with -6 equal to 0. -6 plus 6. What we do to one side, we do to the other side, plus 6. X is plus 6. Yeah? Yeah? And if you want to check it back, plus 6 and all of them, -6, you get your 0. Yeah? So now, the alternative name, we use Roman numerals. So when you see this, and we're not talking the artist now that says, V6. We are talking about this representing it's the link between the oxidation number that we worked out a while ago. Yeah? Yeah? I don't know. My mouse is giving some issues. Well, the pad on the laptop, it just went down by itself. It says, determine the oxidation number of nitrogen. See another problem, Yuta? Nitrogen. And give an alternative name for the ion. Ready? What are the rules we can apply here?
The same one for oxygen.
All right. Which is
-2.
which other one?
Then hydrogen ion.
I'm not sure if someone said something, it was really low, so I didn't hear it.
The sum of oxidation number of a polyatomic ion is equal to the charge of the ion.
Wonderful. So we can apply those rules, two rules. See why rules are important so we can utilize them. So we know we're going to call the nitrogen X, said that the sum of them, we know oxygen is a -2 and we have two of them. And when we add them, it should equal to the charge, which is -1. So we end up with that. We end up with that. So we want to get X by itself, we add 4. If we do that to one side, we have to do it to the other side. X is a positive 3. So you see nitrogen, I'm still in this polyatomic ion, it assume a positive. And that's why I said those ones, those are the ones that CXC will actually normally ask you about. So normally we know we have nitrite and we have nitrate. But we still can call both, sometimes we refer to both of them by saying the nitrate, right? So this is nitrate and we have the 3 in bracket. If you do it for the, well, so this is the nitrite, right? But we can call it nitrate 3. So if we work out that of the night, and you can do that one for me. So if you work out the nitrate, we still would call it the nitrate, and then you would have the oxidation number in Roman numerals in bracket. All right? So, sorry, you can work out that for the nitrate and tell me what you get when you do so. Determine the oxidation number of chlorine in the chlorate ion. So again, we would have been assuming that this is a -1, not true. But watch what happens. What is the rule that we can use here? So we want to find this. What's the rule? What's the rule?
The Cl will be 0, and no, the same one for oxygen,
Thank you.
-2, and I don't know if that's a neutral compound.
So you're not seeing it? So helper guys, is this a neutral compound?
No, sir.
And if it's not a neutral compound, we know that
It's a bonding.
when we add it, it should equal to, just as it's similar to what we just did a while ago now. The same two rules that we use to do this
Right.
are the same two rules. So again, I want you to get familiar so that you can just be on the ball. You're supposed to just, I know we're just learning it. So again, as we go along and you get the practice, you're supposed to just get right at it. Sometimes you can even, and I can tell you, when you reach a stage, you can actually just look at this. You don't have to go over here and work it out. You can look at it and just know the oxidation number, the chlorine right away. Maybe persons in the group can do it or on the meet can do it. It also has an implication for your math. So if you know a little bit of, how to deduce numbers, you'd be able to do it quickly. So we know X, we call in the chloride X plus. We have 4, and each of them is 2. And then we said it should be equal to -1. Don't know what is updating on this thing. I hope it doesn't shut down. So 4 times that, we get x x minus 8 equal to -1. To get rid of or to have x by itself, we add 8. And if we add 8 on one side, we do it to the other side. And so x is, right? Yeah? So the chlorate 7 ion. Cool? So again, just remember that the name of it, what I want you to note, the name is a reflection of the oxidation state. And we use Roman numerals to deal with that. Yeah? So quickly, we said to determine the change in oxidation number of nitrogen in the following reaction, and use this to deduce if the ammonia has been oxidized or reduced. So quickly, look like we see the equation here already, don't it?
Yeah.
Right, we actually started out with. So just to deal with, remember we don't have to go do everybody, because the question really just a focus on the nitrogen. So let's focus on the nitrogen. As the oxidation number, we can start by dealing with the easier one. What is it for this and why?
0.
Why?
Because it's not bonded to anything.
Wonderful. Not any other element. What is what we know about here? And again, we should be able to, what if we're looking for the nitrogen, what 2 rules we can use to help us? What 2 rules we can help us to deduce what is it for the nitrogen here?
Hydrogen has a oxidation number of 1.
All right. You said the hydrogen, right? I didn't hear you clearly, but I'm hoping that's what you said. The oxidation number for the hydrogen is 1. Yeah? +1. What type of compound is this? We seen any charge? Talk to me now, guys. Are we seeing any? Is it that it's too small? You can always increase the size. Better?
So, so it's a neutral compound.
Wonderful. And if it's a neutral compound, we know that when we add all the oxidation number of the atoms involved, the sum of all of them, it should equal to 0. Now, again, even though one hydrogen is a plus 1, we have 3 of them. So technically, it's a 3 plus. And again, these are things. So as you move forward, you can actually start to look at them. So you see Mr. Nitrogen again, Hop Ghana, -3 as its oxidation state. So we're moving from -3 to 0. We know that this is a what? What happened to the oxidation state?
It decrease,
Sure?
increase,
So it increases. And what's an increase in oxidation state?
Oxidation.
Go again.
Oxidation.
So oxidation. So definitely the ammonia is being oxidized. Yeah?
Yes, sir.
All right. I know it is 10 past 6. So you can always, we're at 50. You can always continue, but we will finalize oxidation and reduction next class and close off on it, and then move on to electrolysis, which is a pickup from um, oxidation and reduction. So one prerequisite is for you to be able to write half equations for electrolysis. You should be able to identify oxidation and reduction. So again, that's why the topics come in this. I'm doing it in this order. Right? So you need to know oxidation and reduction for electrochemistry. So I hope it was beneficial. We did a review. We looked back at how we deal with oxidation and reduction. We started to answer some of the worksheet questions. Again, we're preparing you for your exam, and we want to say a big shout out to our sponsors. We want to highlight D&J Document Center. We want to highlight Elite Detailing, Evergraphics Photo Studio. Thanks for the continued support. Remember to like and share and comment. How was this topic for you? And remember, Mr. Thomas here, Buckle Down Tutoring Service. Until next time.